Welcome to another GC Basic demonstration. This is part 11 for the PIC16F legacy family using I2C discovery. Let's get into it. So, using the latest build of GC Basic, it's January 2025, and this applies to the 16F legacy chips, 10F legacy chips, 12F legacy chips. Oh, and actually, this is important to understand. This is different from the newer chips. Same public commands, you just need less configuration of the chip. But with that less configuration of the chip in legacy chips, you end up with less flexibility. Like and subscribe to the video, give it a thumbs up, let it run all the way through, please. So what we're going to do is use I2C with serial to discover devices. Let's get into it. I've assumed you've got all the prerequisites. You've installed the software, your programmer is working, you've got a PIC attached, you've got some LEDs, you've got a pot, some switches, and a USB TTL, which is quite important because we're going to send data to a terminal. You have an LCD. That's the thing that we've been building up so far. The board I'm using is a PIC-M2 Plus demonstration board, and I've got the serial hooked up into a particular port, and you can put it out through the port 3 shown on that diagram. I will bring up a pen. However, I've got it hooked up to junction. What is it? Let me have a look. 18, J18. Here, I've got it hooked up. I'll show you that on a video stream now. Here is the chip, LEDs, LCDs, sound, external EEPROM, temperature sensor. Serial connection is just here on junction 18. I also have a ground connected, and there's a TTL converter hooked up here. And we're going to send some data down there. So what it's going to do, we're going to send out a discovery and discover all the devices that are on the I2C bus. Clever. So what have I got hooked up? Well, I've got the SDA on port 3. No, I've got the SDA on port C.4 and the clock SCK on port C.3. I can't change those. This is a legacy chip. With the newer chips, I can change where I put those, but on here, it's locked to those ports, so I can't put them anywhere else. If I'm using the hardware I2C routines, I have to pick these ports. I have no other choice. Should we look at a data sheet? We've got a data sheet for this. I'm going to go into PIC info. Here we go. That's the ports I've got to use, but I'm going to go into PIC info and pull it up. So let me get into the IDE for a second. Function key F4. Type in PIC info and bring it up. Oh, it's already running somewhere. There we go. It's on the screen already. I'll zoom in. There we go. If I go to select the front tab, and it says data sheet, click on that, and it will open up your default browser with the data sheet. That's fantastic. You can see that on the screen, sort of. Let's zoom out. If I come down to set the tables in here, oh, here we go. I'm going to use the PDIP chip. Here we go. Here's the PDIP there. Look, there you go. Look. That's the one there. Look. Let's zoom in on that. Here we go. Look. RC4, RC3, and it says SDA, serial data, serial clock. So that's the ones we need. SLC, SCK, SDA. So they're locked on here. If they had a little number behind them like that, I could move it, but I can't. And that is the big difference between these legacy chips. They're locked to particular ports. As we saw previously, TX, RX are locked to RC7 and RC6. This time we are locked on RC4 and RC3. We can't change it. So back in my PowerPoint, that's why that box is there, because I'm drawing your attention that they are locked in there. What have I got? We'll have a bit of fun. I'm going to show you an LCD, GLCD later on, but this is how it must be set up. The circuit must be set up as follows. You have VCC. In my case, that's 5. Let me do a little diagram. 5 volts. I have ground, but I must have pull-up resistors here and here. Now, you can use the internal pull-ups inside the chip. I don't, because I need to know that the connectivity is perfect. I don't want to use some internal register to make sure it works. And typically I use 4K resistors, 2 4K resistors, and that's this one here and here. And they both, it needs to be pulled up. They've been pulled up on the SCL and SDA, and I will change my PowerPoint. SCL, look. Let me go back to my PowerPoint. That is incorrect. I will change that before I publish, okay? All right. It should be SCL. Then you connect, those lines will be then connected into your I2C devices. So yellow, I typically use yellow for the bus, for the clock line, sorry, and the blue for the SDA. That is important. No pull-ups, no worky. And we have a set of public I2C commands. I2C start, I2C send, I2C stop, I2C restart. And they're all in the help. So we're going to see them live, but if you want to know what the software ones are, they don't start with H. All the hardware ones start with H. So we have start conditions, which is a transition of the SDA and SCL. We send some data, send more data, and then we send a stop condition. It is essentially a green, then some data, and then a red for a stop. And if you have a protocol analyzer, you could see all this magic happening in the background on the protocol on the wire. What we're going to do is we're going to send some commands out, and we're going to send a command out to each of the potential addresses, and they're normally 0 to 256, and we're going to send out an address to 0, 0, and if it responds, we know there's something attached. And so in this demonstration, it says 9A and A0 has something attached. So something on that board has those addresses. And if you don't get that back, that's because you either haven't got a pull-up or you've got the wrong connectivity. Something is wrong. I believe it's important to get this display before you do any I2C operations. Do IC squared discovery. Make sure the bus is working. So let's set up the I2C and review discovery results. Let's get into the lab. IDE. Open up the Explorer. 170, show I2C devices to the serial terminal. Now, Control B to get rid of that. I've got my terminal set up. It is hooked up. I'll disconnect it, rescan. Let me zoom in so you can see all that. I'm going to rescan, make sure it's the only one available. It is, connect it up. Check my baud rate is 9.6. That's good, that's excellent. That's what I want. And then in my header, I need to tell it where things are. Now, the 4 things you need to tell it is where the data is, where the clock is, what the baud rate is, and it's a master. So we do the first 3 with constants called HI2C underscore data, and then a port. The same for the clock, a port, a baud rate. Use 100 for discovery. You can use what you like, but not every device works faster than 100. So do discovery at 100 and then increase it if necessary. Then you need to tell it that there's your hardware I2C mode is master. You're a master. You're in charge of the bus. There's a slave option, and inside the demonstrations, there is a very robust how to write your own slave. But we're using a master. And so once you've done that, it will then initialize the lines for you. It will make them inputs as required, and then it will then say, I am the master. Let's just look at what's going on. Can we ignore for now anything that starts with HCL print? That's just screen formatting for us. It's just screen formatting. And so we're going to format the screen. We're going to make a nice little box on it. We've seen boxes of data appear in the past. Actually, if you look at the PowerPoint, it will be stronger. It formats this table on the right-hand side here. It gives us the header, the verticals, and all these dashes. Let's look at the meat of the code, the real meat in the code. The real meat in the code is here. It says, do a start, send out a start signal, which is the transition of the clock and the data line. Send out an address. Well, there's a forward next loop, which is device ID, and that is 0 to 255. So that sends out something. Then you have to send out another byte. That's because if you're doing a read operation, you can do a write or read in I2C. You have to send out a 0 to make sure everything's happy, and then you do a stop. And then there's a public variable called ActPollState. And if the ActPollState is set to false, then you know there's something on that bus, on that address. If not, put a dash up there. Let's program that. Let's bring up the terminal. Is it connected? It is. I'll put it on the screen so you can see it. It's programming it at the moment. And it says there is something on address 9A and A0. Well, isn't that fancy? But that's because if we look at the desk cam, I've already said there's a piece of EEPROM sitting here. That's external EEPROM. And right down here, I think that's a temperature sensor. And we can have a look at that. So why don't I disconnect those two? I've just taken off these two here, look. And then I'm going to rerun the terminal software. So let me go back to the screen so you can see it. Push the button. A0. Obviously those buttons weren't the ones I was looking for. Yeah. Nope. Those weren't the ones. I should check the documentation. So what I'm going to do, I'm going to do something live in preparation for the next demonstration. I'm going to pick up, I'll go back to my camera, desk cam. Where is it? What's that? That's a I2C device. I'm going to hook that in. I'm going to hook it into here. Essentially do this, put some power on it, and we will get some magic. Haven't got prepared for this really, so I'm going to sort of do this live. Let me just grab some cables. I just want some wires. Let me just pull this up. One, I want a red, I want a green, and I want a blue. And what I'm doing here is I've just got some DuPont VCC. That's going to be 5 volts. That's going to be my ground, the green. I've already said I use blue. I use blue for the data. The next one is I use yellow for clock. It just makes it easier in my brain to remember things. So I've just connected it up. That's 4 on there. At the other end down here, I need 4. I'm going to put the ground on first. I'm going to put some ground. Yeah, there's ground there. And we're not going to see it. We're just going to see discovery work. And then I've got, and I am going to check my documentation. It should say SCL. I'm so sorry, you can't see what I'm doing. I'm just putting that back to what it should be. That should say SCL. SCL is on 3. SCL is on 3. Watch an old man do this. SCL is on 3. I'm going to put 4 in first. Bit tricky this. I'm going to have to put that one in first. 3 and then 4. We're connected up. Check my connections. All looks good. Shouldn't do things live really. Back into the terminal. And that tells me I have nothing working correctly. So probably I've got the bus inverted, but I will do a reset, the whole thing, and then just check. I'll reset the board, and it's not happy. We can see it's not happy. I just connected something up, and I probably got those inverted. Let me check my connections here. SDA is on blue. Let's see, have I got it on the right one? 5, 4, 3, 5, 4, and 3. RC4 is the data. Hey, voila. We have a 78, and that's the address of that GLCD. It's working. So what I did, I had it incorrectly wired up. Now I know the bus is working, which is absolutely perfect. I can push the button here, and magic happens. It just runs it again. I'm going to power cycle the whole thing, and I now know that I've got an address on 78, an address on 9A, an address on A0. And I know that 78 is a GLCD, 9A must be the temperature device, A0 must be the memory. Let's go and look at the data sheet for this product. Pick them board folder. I put that in the resource folder. That's there. Let's have a look at the addresses. A0. I'm just doing a search for address A0 in the documentation, and it says, I can't see it there. Isn't it great? It's picking up the search on A0. Oh, that's really good, isn't it? Temperature, temp. I'm doing a search for temp. It actually might be undocumented. Knowing microchip, yeah, it's undocumented. Fantastic, hey. You wouldn't know what the addresses were without going through all their source code. Very, very poor. But never mind, eh? Am I surprised? Not really. Let me have a look at the documentation. It might be in here. I'll just rotate the PCB. We'll look at the PCB and zoom in on that. See if we can see the addresses. Zoom in. What's that? That's the power. There's something here. That looks like a U5, whatever U5 is. Must be one of the devices we're looking at because it's got the SCL. It's got the, if I bring it into the camera would help. It's got the SCL and the SDA, which is clearly a I2C device. Where else? Where else is the I2C on here? We know there's a temperature sensor that was there. Oh, here it is up here. It's a 256 memory device lot. So it's an external EEPROM, which is great. You can use that. It's out on C4 and C3 correct. And they've used 4.7 polyps, which is interesting. But again, I'm going to do a search on the LC256 and see if there's any documentation on the address. Not that I can find. Oh, wait a minute, look. It says 256. I'm just doing a search on it. It just says here it's connected to the bus. There you go. Oh, here we go. Look, it has an address. It has an address. That's the temperature sensor. Let's look at that in a calculator. Now, it's address 4D, and that's a 7-bit address. So if you just shift that to the right, or the left, sorry, or multiply it by 2, the address is 9A, and that is quite correct. So we used 8-bit addresses, and that is documented as a 7-bit address. So we now know that we've got I2C devices. They're sitting on 78, 9A, A0. You can write to the external EEPROM using the external EEPROM library. There's a temperature sensor here, and now there's a GLCD sitting there, which is fantastic, which we will use extensively. So let's go back. This is video 11. We're going to be using a GLCD device to show you some of the GLC public commands. It's quite good fun, and we'll do that in the next video. So enjoy.